What are antiderivatives? Antiderivatives are the inverse operations of derivatives, or the backward operation which goes from the derivative of a function to the original function itself, in addition with a constant. Mathematically, the antiderivative of a function on an interval is stated as f antiderivative x equals f of x, for all x is an interval.
If the function f of x has a derivative, then it's called definite integral, or antiderivative of f of x. The antiderivative of a function is not unique. All of them are antiderivatives, or f of x 3x to the second power, due to they are included in f of x to the third power plus c, where c is called constant of integration.
The indefinite integral of f antiderivative x is represented by the following expression. The function f antiderivative x is called integrand. The integral of a function is an algebraic expression whose derivative is the original function. This is why we call it antiderivative of the functions.
In order to get the antiderivative of the problem in example number 1, we first need to get rid of those roots that are on the denominator of the first two fractions. So in the second line, we see how the denominator that was the square of x translated into a negative exponent of x, which is a half. Now we need to leave negative 5/3 alone and just fix the cube root of x to the fourth, and that ends up being a negative exponent of x, which is 4/3. We leave the other two negative variables the same as they were before because we weren't trying to get any antiderivatives yet, so they just stay exactly the same, the last two. Now, in the second step, we now are trying to get the antiderivative. The first thing that we need to do is add 1 to the exponent. So in this case, we had a negative half, so we add 1 and that becomes a half. And what happens when we divide 4 by a half? Well, the answer would be 8, and that's what we get. The next variable has an exponent of negative 4/3. We add 1, that becomes a negative third. Then the negative 5/3 x is divided by a negative third, and that becomes positive 5x. Next, we have negative 6/5 x squared. We add 1 to the x squared and it becomes x cubed. The negative 6/5 are divided by 3, so we end up with negative 2/5. Now, something that we always have to do when solving for the antiderivative is add an x to the last variable of the function. So we had negative 2p and it becomes negative 2px. Also, it's important to notice that all the exponents have to become fractions again. So if, for example, we had the exponent of a half, that has to go back to being a denominator and a square root. Last thing is that we always have to add plus c because there could be a number that there's no possible way we know which number it is. So we add plus c representing that number.
For a real-life application of antiderivatives, we will be working with rates that could be given in different word problems. We can know it's a rate because it uses fraction units. For example, it could be miles per hour, people per minute, etc. Here's an example of real life. we have the table with the x-axis being time and the y-axis the amount of buses. Here's a function that represents the rate of change. After being given this piece of information, we can conclude that f of 2 is equal to 7. When we add up all the change through solving the equation, which gives us the change of the rate, which is equal to the amount of buses, we can get the answer of the total amount of buses after 6 hours.